Okay, Assalamualaikum and good morning, everyone.
Selamat pagi, Dokter.
Okay, so today we will continue on tutorial 11 that I skipped last time, question number 2. And then we will continue on lecture 5A, should be 5A, on compensator. Okay, so let's look at this question. So the forward transfer function is GS GS equals K times S plus 5 and then S squared plus 8S plus 80. Okay, so firstly, we need to find the poles and 0. So the poles will be solving the denominator. So we will get S equals 0 minus 2. And then the last one, you can use calculator solving the quadratic equation. So you get negative 4 plus minus 8j. And then for 0, we have 0 at minus 5. So here we have 4 poles and 1 0. So meaning that we have 4 branches. And we know that one of the branch will go to 0 equals minus 5. And the other 3 branches will go to infinity. So we add 3 more infinity 0, just to indicate that one of the poles will go to one of the 0, and the other 3 poles will go to infinity. And then from here we can calculate the asymptote. So asymptote so we can find the real axis intercept. So the formula is sum of poles minus sum of 0 divided by number of poles minus number of 0. So we get 0 minus 2 minus 4 plus 8j minus 4 minus 8j. Okay, so these are the poles. And then divided by, minus 0. So 0 is minus 5. Divided by number of poles. So number of poles, there are 4. Minus number of 0, 1, 0. So solve this, you get sigma A equals negative 5 over 3. And then you can calculate the angle of asymptote using this formula, 2k plus 1 times pi over 3. So we start with k equals 0. Not over 3, over number of poles minus number of 0. Or you get 2k plus 1 times pi over 3. So at k equals 0, you get theta A equals pi over 3. Then repeat the process. At k equals 1, you get theta A equals 3 pi over 3 or pi. And then k equals 2, you get theta A equals 5 pi over 3. And then at k equals 3, you get theta A equals 7 pi over 3. So this is more than 2 pi. So we don't take this value. Okay, we stop calculating at k equals 3. So there are three asymptote only. Okay, 5 pi over 3, pi and 5 pi over 3. Now you can sketch first the poles and the asymptote on the S-plane. Okay. So we have our pole here. -2, -4, and then sekejap, So somewhere here, 8j minus 8j here. And we have poles here and here. Okay, so this is not a pole, sorry. And then 0 at -5. Okay, and then we can determine the location of root locus on the real axis. So from positive infinity to 0, there is no root locus on this axis because there is nothing, there is no pole or 0 at this region. And then from 0 to -2, so we only have one pole here. So there will be a root locus on this region. Okay, because we only have one pole and it's an odd number, okay, odd amount of pole. Then from -2 to -4, we have two poles. So two poles meaning that there is no root locus on this real axis portion. And then lastly, from -4 to -5, or not last, okay, second last. So we have four poles, okay, an even amount. So again, there is no root locus on this region. And then lastly, from -5 to -infinity, we have five total of things, four poles and 1 0. So we have an odd number, an odd amount of number, then we have root locus here. Macam salah je. Okay, nanti kita tengok. Okay, so we have root locus here. Then we can sketch the asymptote on this S-plane. Okay, so asymptote is at -5/3. So it's about 5/3, about 1.67. So it is somewhere here. Okay, sigma A. And then the angle is at pi over 3. Pi and 5 pi over 3. So pi over 3 is about 60 degree. So 60 degree. Then gonna sketch lah 60 degree. So it should be something like this. Okay, so this is pi over 3. And then another asymptote is here on the real axis. Okay, so we get this sketch already. So we can now determine other things like breakaway point or breaking point and the j omega axis crossing. So let's determine the breakaway point and breaking point. So there will be breakaway somewhere here and break in somewhere in this region. So let's determine breakaway and breaking point. So again, the formula is a summation of 1 over sigma minus O equals summation of 1 over sigma minus 0. Then you can substitute. Okay, so the first pole is 0 plus 1 over sigma plus 2 plus 1 over sigma plus 4 minus 8j plus 1 over sigma plus 4 plus 8j equals 1 over sigma plus 5. Okay, so we have this equation that is quite long to solve by hand. So if you use MATLAB or Symbolab, you will get sigma equals negative 1.087 and negative 7.447. Okay, then we can sketch this on the S-plane. So negative 1.087 should be somewhere here. Agak-agak, okay. And then negative 7.447 should be around here. Yeah, and again, agak-agak, okay. Now we can determine the j omega axis crossing. So j omega axis. So firstly, we need to find the closed loop transfer function. So here you will get k times s plus 5 over s plus 2 and then take the denominator and try to kumpulkan. So we get s power of 4 plus 10s cubed plus 96s squared plus 160 plus k times s plus 5k Then you can generate the Rutherford table. So we get 1, 10, 96, and 60 plus K. Then 5K, 0. Then find S squared. Okay, you use the determinant. Then here you get 5K. Then S1, again determinant. So you get K squared minus 140K. So here you get 0 and 0. And then the last one for S0, you get 5K here and 0. Then to find the K value for at J omega axis crossing, you use S1. So from S1, solve this value here, equal it to 0. So you get K squared minus 140K minus 12,800 equals 0. So you will get two value of K. So you get K equals 434.56 and negative 294.56. So here, because we get two value, so only one value of K is for the K for the J omega axis crossing. So we take the positive value. So we take the positive value, then use this on S squared. So substitute in here. So you get 800 minus 434.56 over 10 S squared plus 5 times 434.56 equals 0. Then you get S equals plus minus 7.71 J. Okay, so this is the J omega axis crossing. And this is the gain at J omega axis. Now we can sketch this value on S plane. So 7.71 should be somewhere here or here. Let's say I label it S1. Okay. Then apa lagi? Tak ada dah. Okay, and then we can find the range of K. So for the range of K for stability, I want you to try by yourself later, okay? So find the range of K for stability. So this one you try for yourself. by yourself, and then you can, if you want to check, you can refer to me. Okay. Okay. Now we need to determine the angle of departure, because we have um, complex pole here. So we have angle of departure. Perhaps I determine it here. So angle of departure. First, you can sketch the location of all of the poles and 0. And then you determine the angle from all of the poles to this pole here. So first angle is here. Let's say theta P1. Then theta P2. Theta P3. And then this angle is 0, theta Z1. So let's determine theta P1. So theta P1 is, you can use 180 minus tangent minus 1. So this length, this height divided by this length. So you get 8/4. So this equals 106.56 degree. And then theta P2. So again, you can use 180 minus tangent minus 1. 8/2. So you get 104.04 degree. And then theta P3 is just 90 degree. And then theta Z1, you can use tangent minus 1. This height divided by this length. So it's 8/1. You get 82.87 degree. So lastly, then angle of departure equals 180 minus the sum of angle from poles minus sum of angle from 0. So 180 minus 116.56 minus plus 104.04 plus 90 minus 82.87. So you get negative 47.73. So it's a negative, meaning that it measures from negative, clockwise. So change it to counterclockwise by adding 360. So you get 312.27 degree. So if you can sketch this angle on S-plane, so the angle should be about here. No, sorry. Okay, so the angle should be here, theta. Okay. Okay, so we get everything already. Then we can sketch the root locus. So we know that we have 4 branches. So one branch will go to -5, and the other 3 branches will go to infinity. So we have S1 here. S1 is the S1 and S2 are the j omega axis crossing. So if you want the root locus to cross this crossing, you must make sure that the root locus will cross this but not crossing the asymptote. So what I'm trying to say is that oh my god, semua hilang. So what I'm trying to say is that yeah. Okay. Okay. So if you want to sketch the root locus from here, from this point here, and then cross this j omega axis crossing, then you will realize that it will cross the asymptote. So the root locus coming from this breakaway point here is not the one that crossed this j omega axis crossing. So the root locus branches that cross this j omega axis crossing comes from somewhere else, okay? Not from this breakaway point here. So it might come from these two poles here. So we know that three poles will go to infinity. Three poles will produce branch of root locus that goes to infinity. And we know that the branches are not coming from these two because it will cross the asymptote to cross this j omega axis. So therefore, the only branches that can cross this j omega axis will come from these two poles here. So we can roughly sketch this, and it will look something like this. Okay, so the two branches of the root locus coming from these two poles here will cross the j omega axis, but it won't cross the asymptote. Okay, so if you extend the asymptote, these branches will not cross the asymptote, but it will reach infinity. Okay, so how about the other two poles here? So the other two poles here, one of it will go to -5, and the other one will go to infinity because we have this portion here on the real axis that extend until infinity. So the shape will look like a circle. So we have a circle. And then one of the branch will go to -5, and the other branch will go to negative infinity. Okay, so the root locus will look like this, and you can check the shape, the actual shape using MATLAB. Okay. Okay, so that's the end for root locus. Any question before we move on to compensator? Okay, so if you have no question on root locus, I hope you can try do your project and try to understand how to calculate all of the properties for root locus. Okay, because the question will definitely coming out in your final exam on how on sketching the root locus. Okay, so let's move on to this lecture, which is about compensator. Okay, so today's lecture is about compensator. So we are now on lecture chapter 5, 5A compensator. So after completing this lecture, you will be able to understand the purpose of a compensator and then design phase-like compensator and also design phase-lead compensator. So here we have two types of compensator, lag and lead compensator. Okay, so before we can go into designing compensator, we need to go back to what we have learned on second order system, okay, time response of second order system. So on second order system, we can calculate the percent overshoot using this formula, okay, percent overshoot equals 100 times exponent of negative damping ratio times pi divided by square root of 1 minus damping ratio squared. Then you can also find the damping ratio by using this formula. Then we can determine the damping ratio from the S plane, okay, the position or the location of the second order system poles. So if you have two poles here, then you can find the angle theta that make this line towards the pole. And then the angle equals cosine minus 1 of damping ratio. And then the real axis value of the pole is negative damping ratio times omega n, or equals the real part of the poles. And then the positive, the imaginary part of the poles will be this omega n times square root of 1 minus damping ratio squared. Okay, so this is actually formula. Okay, later on we will use this, and I hope that during exam you can just refer back to this slide. Okay, and then some other important performance parameter like settling time TS equals 4 over damping ratio times omega n, and then the peak time equals pi over omega n times square root of 1 minus damping ratio squared. Okay, so all of this formula we will use a lot in designing compensator. Okay, so before we go into compensator, let's go back to the design problem. Okay, so a root locus allows us to choose a proper gain K to meet a system performance specification. So what does this mean is that we can adjust the value of K to get a suitable performance for our system. Okay, so that's why we have the root locus. So as the gain K is varied, then the system response also varied, okay, or change depending on the position of the poles and zeros. So if the poles and zeros are on the right hand side of S plane, then you will get an unstable system. So if the poles are located on left hand side of the S plane, then you get a stable system. So the system performance is limited by the shape of the root locus that you sketch or you get from MATLAB. So if you sketch the root locus from MATLAB, then the system performance is limited by the location of poles on that root locus. So what does this mean? For example, if you have the blue line here, so the blue line on the first figure here represent your root locus. So at a specific percent overshoot, so let's say this black line here that cross A and B are the diagonal line that you use to find the percent overshoot. So the system performance is represented by the crossing with the root locus at point A here. And if you sketch the time response of this point A, then you will get the time response shown on figure A here, the blue curve here. Okay, so let's say if you want the system to behave similar to point B, which is the black curve, you cannot obtain this using this root locus because this root locus in blue color will never cross point B here because point B is outside of the root locus. So if you adjust the K value, the gain K value, whatever you did, it will never cross the point B here because the point B does not lie on the root locus or not on the root locus. So what we can do if we want to, if we want our system to behave similar to point B, so we need to do something. We need to add something to the system, which is the compensator or the controller. So we can add compensator and controller to change the root locus, to change the shape of the root locus such that it will cross point B. So here we can use compensator. So to improve the system from point A to point B, we can do this by replacing the existing system, or we can remove the existing root locus and produce a new root locus. Okay, but doing this, basically we just scrap over the system or change the plan or change the process, which is usually very expensive or not productive. Environment like in power plant, for example, or in designing uh, robotic control, for example. Basically, removing the plant or process is like creating a new things, like create new robot so that it behaves like point B, or create a new power plant so that it behaves like point B. So this is very expensive and not productive. Okay, so to achieve the system from A to B, we can add a compensator that the compensator will have additional poles and zeros so that it will change the system root locus to intersect at point B. So we have many types of compensator. So we look at the cascade compensator. So we focus our design only on cascade compensator. So there are many types of compensator, but because cascade compensator is the easiest one to understand how it works and how it can improve a system performance. So the first type of cascade compensator is the ideal integral compensator. So given a system with a desirable transient response with close to poles at A, so let's say you have these poles at A, and then the total angle of all poles and zeros at this point is a multiple of 180. So this is what we have learned back in lecture 4C, root locus, introduction to root locus. Any point on the root locus will have the sum of angle equals multiple of 180 degree. Okay, so meaning that this point will be on the root locus. So let's say if you add a compensator, which is this K over S here. So let's say if we add a pole on the compensator. So if you look at this compensator, K over S, then the pole for this compensator is at 0. Okay, S equals 0. So if we add a pole at 0 here, theta C, then the angular contribution of the new pole will cause the angle at point A to be no longer equal 180 degree, meaning that the point A is now outside of the root locus. And so the new root locus will not behave similar to time response at point A because this point A is not on the blue curve here. So let's say if we add another 0, let's say we add s plus a on the compensator, or we add a 0, the value of a as close as possible to the pole theta PC just now. Let's say the 0 is at here, and the angle is theta ZC to point A. And now the point A can now be on the root locus. If we calculate all the angle, then we can get the point A as close as possible on the root locus. Okay, so that's why here almost equals the root locus. Under 80 degree. So here, if we add theta PC and theta ZC, or the new pole N0, then we can get a new root locus, and that new root locus will cross at point A. So we have a similar system behavior as when there is no compensator. Okay. Okay, so let's look at an example. So let's say if you have this system, K times the plant, gain K times the plant. So given a system above with transient response requirement, damping ratio equals 0.174. So show that the addition of an integral compensator, PC equals 0, can reduce the steady state error while maintaining the same transient response. Okay, so we want to add a compensator to reduce the system's steady state error, but we want to maintain the same transient response, which is the damping ratio equals 0.174. So this is some calculation, but I don't think that this calculation will come up in final exam. This is just to show you how to get certain values from the example, okay? So let's say if you sketch the root locus, okay, and then you find the poles at the damping ratio 0.174. So you can find the pole at this point, negative 0.694 plus 3.926 J. You can do this in MATLAB. If you refer to project part 4 later, it will teach you how to determine this pole at this damping ratio. Okay, so this calculation is just a manual calculation example on how to determine this point. Okay, so at this point, the gain K is 164.6. So the system is type 0 because on the plant, we don't have, we have S power of 0 at the beginning here. So the system is type 0. So the system will have a steady state error only when you use a unit step input, okay? Or you have steady state error for KP, for static or error constant KP. So this is go back to lecture 4B, steady state error, okay? So to find KP, you use the limit theorem. So you get KP equals K over 20. And then to find the steady state error KP, the value of KP, you use K from the intersection that you obtained just now from the root locus or from MATLAB or from manual calculation. So you get KP equals 8.23. And to find the steady state error, you just use the formula from lecture 4B. Okay, so steady state error equals 0.108. Okay, so this is the root locus from previous slide. So basically at this point here, at this root locus here, poles on the root locus, you get k equals 164.6, and the system response will be having steady state error 0.108. Okay, you can try to plot this in MATLAB and see the system response, okay, the time response curve. And then let's say if you want to improve the system steady state error. So the steady state error just now is 0.108. So let's say if you want to reduce more the steady state error, maybe to make it 0.01, for example, you want to make the steady state error even smaller. So you can add a compensator. So if you add a compensator, so here this example, add a compensator at pole equals 0 and a compensator 0 ZC to be somewhere near PC, okay? So here ZC chosen as negative 0.1. So this is the compensator. So you can sketch the new root locus using MATLAB. So this is the new position of poles and 0. And then you want the system to behave at the same damping ratio. So at the same damping ratio, it will cross this line here at negative 0.678 plus 3.837 J, and the gain is equals 158.2. So now the system, the overall system type has become type 1 because you have S here. Okay, so this S is S power of 1. So if you combine the two transfer function, then the system will become type 1. So what is the Kp at steady state error? So for type 1, Kp equals infinity. And because Kp is infinity, then steady state error becomes 0. So now what we can see is that if we add this compensator, then at the same damping ratio 0.174, the system will have 0 steady state error. So from previous example, without compensator, or system without compensator, our system at the same 0.174 damping ratio, we got an error of 0.108. But now if we add a compensator at the same damping ratio, the steady state has been reduced to 0 because basically we changed the type of the system, okay, by adding the compensator. Okay, so that's the effect of compensator, which is one of the effect is eliminating the steady state error while maintaining the same transient response. So if we sketch the time response curve for system without compensator and for system with compensator, by adding the compensator, we can see that the steady state error has reduced from this black color here, which is 0.108, to a new blue colored here to steady state error equals 0. So that's the effect of adding compensator. Okay, I think that's it for today. We will continue the lecture on next week on the calculations. Okay, so what I want you to do now is to try to explore project part 4. So we have project part 4. So on project part 4 is about designing compensator. So I want you to explore that as well while doing project part 3, root locus, okay? So they are basically related to each other. So when you understand how to sketch root locus, so when you do project part 4, you can understand how to adjust the root locus to get a stable system. Okay, so I want you to explore project part 4 as well, so that for next week lecture, you understand the concept of compensator and how to adjust the root locus to get certain characteristic of the transient response. Okay, so that's it for today's lecture. And next Monday is holiday. So see you again on next Wednesday, inshallah. Assalamualaikum and goodbye.
Thank you, Doctor.
Thank you, sir.
Thank
Thank you,
you.
Doctor.
Thank you, sir.
Thank you.